Picture this: a longship cutting through the frigid North Atlantic, surrounded by nothing but endless gray water and a sky heavy with storm clouds. The wind howls, the waves crash against the wooden hull, and visibility drops to almost zero. For days, there is no sun, no stars, no familiar coastline, only the vast, terrifying unknown. Yet somehow, against all odds, the Vikings not only survived these journeys but thrived, crossing thousands of miles of open ocean to reach places like Iceland, Greenland, and even North America, 5 centuries before Columbus. How did they do it? Without compasses, without maps, without any of the tools we take for granted today. How did these legendary seafarers conquer the most treacherous waters on Earth? The answer lies shrouded in mystery, whispered in ancient sagas, and hinted at in archaeological fragments, a secret so powerful it feels almost like magic. That secret is the sunstone. For centuries, the sunstone has remained one of history's most tantalizing maritime puzzles. Mentioned in Viking lore but never clearly described, this mysterious navigational aid was said to have the power to locate the sun even on the cloudiest, stormiest days. To modern ears, it sounds like something out of myth, a crystal with supernatural abilities, guiding ships through impenetrable fog and endless nights. But what if it wasn't myth? What if the sunstone was a real, sophisticated tool, born from an intimate understanding of nature and light, one that allowed the Vikings to achieve the impossible? This isn't just a story about navigation. It's a story about human ingenuity, courage, and the relentless drive to explore, no matter how daunting the challenge. In this video, we're setting sail into that mystery. We'll venture back into the world of the Vikings, not as barbarians, but as brilliant innovators who mastered their environment in ways we're only beginning to understand. Together, we'll explore how sunstones might have worked, why they captivate historians and scientists alike, and what they reveal about our deeper longing to conquer the unknown. This is a journey into the heart of one of history's greatest adventures, a tale of stormy seas, ancient wisdom, and the enduring quest for discovery. So come aboard. Let's unravel the enigma of the Viking sunstone and discover how a simple crystal may have changed the course of history forever. So what exactly was this legendary tool? Let's move from the stormy seas into the world of the sagas themselves, the ancient stories that first gave us a glimpse of the sunstone. These aren't just myths, they're historical records filled with clues. In one particularly compelling tale, the hero Sigurd is navigating under a heavy, snow-filled sky. The text tells us he was able to locate the sun using a mysterious solarstein, a sunstone. This crystal didn't need a clear sky. It revealed the sun's position through total cloud cover and even just after sunset. That's the core of the mystery, a device that seems to defy the very limitations of human sight. But if it was real, what kind of crystal could possibly do this? After decades of research and debate, scientists and historians have narrowed it down to 3 primary candidates, each with a unique and fascinating property. The first, and perhaps the most famous, is Iceland spar. This is a completely transparent form of calcite that has a remarkable ability to split a single beam of light into 2. This phenomenon, called double refraction, creates a telltale doubling effect when you look through it. For a skilled navigator, rotating this crystal until the 2 beams of light align in equal intensity could point directly to the hidden sun, cutting through the haze and gloom. The second strong contender is cordierite, a mineral often referred to by its gemstone name, iolite. This crystal acts like a natural polarizing filter. To understand what that means, think about polarized sunglasses. They cut glare from water or a flat road by blocking light waves vibrating in a certain direction. Sunlight becomes polarized as it scatters through the atmosphere, creating a pattern in the sky that is invisible to our eyes but detectable with the right tool. Cordierite changes color, from a pale yellow to a deep, rich blue, depending on how it's oriented relative to this hidden pattern of polarized light. By turning the stone and watching for this color shift, a Viking sailor could essentially see the sun's location painted in shades of blue. And the third potential sunstone is tourmaline, another crystal with strong polarizing properties. While it doesn't display the dramatic color change of cordierite, it shares that crucial ability to filter and analyze the polarization of light, offering another possible method for pinpointing the sun's position. Each of these crystals, Iceland, spar, cordierite, and tourmaline, would have been accessible to the Vikings through trade or natural deposits, turning a piece of the earth itself into their most advanced piece of technology. These ancient texts are our primary window into the Viking world, and it is within their pages that we find the scant but crucial mentions of the sunstone. The most cited reference comes from the saga of Saint Olaf, a king known for his fierce efforts to Christianize Norway in the early 11th century. In one passage, the weather turns against the king with a heavy snowstorm blotting out the sun. The saga author writes that Olaf, needing to confirm the time of day, asked a follower to locate the sun. A man named Sigurður is brought forth, and the text states, "He took the sunstone and held it up, and then he saw where the sun sent its beams through the stone." This is a remarkably practical description. It wasn't used for a grand transatlantic crossing in this instance, but for a simple, everyday need of telling time. This mundanity is what makes it so compelling. It's presented not as a magical artifact, but as a standard tool, a normal part of the Viking navigator's kit. An even more detailed account is found in the Rodulfsdatter, a lesser-known but equally fascinating tale. Here, the hero, a king named Olaf Haraldsson, is testing the wisdom of a farmer's son named Sigurður. The king asks him to identify the sun through a completely overcast sky. The story says Sigurður took a sunstone, lifted it up to his eye, and pointed out the spot in the sky where the sun could be seen, from which light passed through the stone. He wasn't just guessing. He was so precise that the king had a second man verify the location by looking through the stone himself and confirm Sigurður's finding. This passage is a goldmine for historians. It doesn't just mention the stone's existence. It describes a verifiable method. It suggests a specific technique of holding the stone up to the eye and scanning the sky, and it implies that the skill was something that could be taught and validated by others, pointing to a shared, understood practice among certain navigators. We must approach these sources with a critical eye, however. The sagas were written down in the 13th and 14th centuries, long after the events they describe, some 200 to 300 years after the height of Viking exploration. They are a blend of history, myth, and literary flourish, written by Christian authors looking back on a pagan past. So, did the authors include the sunstone because it was a genuine, remembered tool from a bygone era? Or was it a symbolic device, a piece of exotic technology used to highlight the intelligence and almost magical prowess of their ancestors? The context provides a strong argument for its reality. In both stories, the sunstone isn't used for a magical feat. It's used to solve a concrete, navigational problem under dire weather conditions. The authors describe its use in a matter-of-fact way, without fanfare or explanation, which often indicates that the concept was familiar enough to their audience that it didn't require one. It was simply a thing that existed and worked. This casual treatment within the narrative is perhaps the strongest historical evidence we have that the Viking sunstone was more than just a legend. Of these three candidates, Iceland's spar has emerged as the most compelling and scientifically supported explanation for the sunstone's legendary abilities. This remarkable crystal, a form of transparent calcite, possesses a unique optical property that feels almost like nature's own sophisticated technology. The secret lies in a phenomenon known as birefringence, or double refraction. When a single beam of light enters an Iceland spar crystal, it doesn't just pass through, it splits into two separate rays. If you were to place this crystal over a single dot on a piece of paper, you wouldn't see one dot, you'd see two. This mesmerizing effect was well documented and studied for centuries, long after the Viking Age, but it's the practical application of this split that makes it a perfect candidate for a navigational aid. So how would a Viking navigator actually use it on a heaving longship in the middle of a squall? The technique is elegant in its simplicity. The navigator would hold the clear calcite crystal up to the sky and slowly rotate it. Even through thick cloud cover or fog, a small amount of diffused sunlight still reaches the Earth, and this light is partially polarized, meaning its light waves are vibrating in a specific orientation. As the crystal is turned, the two beams of light created by the double refraction will change in intensity relative to each other. The navigator's goal is to find the precise angle where these two beams appear exactly equally bright. When that perfect balance is achieved, the crystal is now aligned directly along the path of the incoming light, pointing a virtual arrow straight back to the sun's hidden position in the sky. It's a method that transforms an invisible atmospheric clue into a visible, measurable signal. The credibility of this theory isn't just based on laboratory experiments. It's bolstered by a stunning piece of archaeological evidence. In 2002, a shipwreck was discovered off the coast of the island of Alderney in the English Channel. The ship was an English warship that sank in 1592, a vessel from a much later era. But among the navigation tools found in the wreckage was a clear, rectangular piece of Iceland spar. It was discovered near a pair of dividers and other navigational instruments, suggesting it was a functional part of the navigator's toolkit. This discovery is monumental because it proves that the use of calcite crystals for navigation was not just a Viking Age theory. It was a practiced technique that persisted for centuries, likely passed down through generations of sailors. While this particular crystal wasn't from a Viking longship, it provides a tangible, real-world link to the methods described in the sagas, showing that the concept was not only possible, but was actually in use in a maritime context. Furthermore, Iceland's spar would have been a resource accessible to the Vikings. While the name might suggest it was only found in Iceland, calcite deposits are found throughout Scandinavia and could have been acquired through trade. The Vikings were master traders, their networks stretching from the Middle East to North America, so obtaining a specific type of crystal would not have been an insurmountable challenge. What's truly fascinating is the intersection of ancient wisdom and modern validation. In 2011, a team of researchers published a study in which they used a crystal of Iceland spar to determine the sun's position with an accuracy of within 1 degree, even when the sun was completely obscured below the horizon. This scientific confirmation moves the sunstone from the realm of pure speculation into the domain of plausible historical technology. It demonstrates that the Vikings, far from relying on myth or magic, may have been pioneering experimental physicists, harnessing the fundamental properties of light itself to conquer the greatest wilderness on Earth, the open ocean. To grasp the true genius of the sunstone, we need to peer into the very nature of light itself. Sunlight, as it travels from the sun to the earth, behaves like a wave, vibrating in every possible direction. But when these light waves enter our atmosphere, they collide with countless molecules and tiny particles. This process, known as Rayleigh scattering, is the same reason our sky appears blue. It scatters the shorter blue wavelengths of light more effectively than the longer red ones. Crucially, this scattering doesn't just change the color of the sky. It also organizes the light, imposing a hidden order upon its chaos. As sunlight scatters across the dome of the sky, the light waves that reach your eyes from any particular point, say, a patch of blue sky 90 degrees away from the sun, are no longer vibrating in all directions. Instead, they become predominantly polarized. This means the waves are now oscillating primarily in a single, specific plane or direction. To our unaided eyes, this polarization is completely invisible. The sky looks uniformly blue or uniformly gray. But this hidden pattern of polarized light forms a vast celestial compass painted across the entire heavens. The orientation of this polarization forms a consistent pattern, with the light waves vibrating in rings that are always perpendicular to an invisible line drawn straight from your eye to the sun. Even on a completely overcast day, this pattern persists in the diffused light that filters through the cloud layer. This is where the unique properties of crystals like Iceland spar or cordierite become transformative. These minerals are not just pretty rocks. They are sophisticated natural instruments known as linear polarizers. Their crystalline structure is arranged in such a way that they act like a gate, only allowing light waves vibrating in one specific direction to pass through. When you hold one of these crystals up to the sky and begin to rotate it, you are essentially tuning this gate, searching for that specific orientation where the crystal's internal structure aligns with the direction of the polarized light in the atmosphere. When the crystal is aligned with the polarization pattern, the maximum amount of light passes through, making that section of the sky appear brightest. When you turn it 90 degrees, the crystal blocks most of that polarized light, making the view through it appear significantly darker. A navigator would slowly turn the stone, meticulously observing these subtle shifts in brightness, or, in the case of cordierite, dramatic changes in color. The point of maximum light transmission, or the most vivid blue hue, reveals the orientation of the polarization. Once you have identified that key orientation from a clear patch of sky, you can trace that polarization pattern back to its source, triangulating the position of the hidden sun with remarkable accuracy. The Vikings, through profound observation and experimentation, learned to read this invisible map in the sky, turning a fundamental law of physics into their most trusted guide. This is where the legend moves from the pages of sagas into the controlled environment of the modern laboratory. While the historical and archaeological evidence is powerfully suggestive, the most compelling validation for the sunstone theory comes from the field of experimental archaeology, where researchers don't just study history, they actively recreate it to see if it works. One of the most pivotal studies in this quest was conducted by a team of researchers from universities in Hungary, Sweden, and Germany, and their findings, published in 2013, delivered a stunningly clear answer. The team's methodology was both elegantly simple and scientifically rigorous. They took a crystal of Iceland spar and, under a completely overcast sky in Hungary, tasked a test subject with pinpointing the sun's position. The participant used the ancient technique, slowly rotating the calcite crystal and observing the twin beams of light created by its double refraction, searching for the precise orientation where their intensities matched. After each reading, the subject marked their estimated sun position on a sheet of plastic. The team then compared these manual estimates against the sun's actual coordinates, logged by a precision GPS and a specially designed telescope. The results were nothing short of remarkable. The navigational error, the difference between the estimated and the true position, was consistently less than 1 degree. To put that incredible accuracy into perspective, a 1-degree error in navigation translates to being off course by just 1 nautical mile for every 60 miles traveled. For a Viking ship aiming for the coastline of Iceland or Greenland, that level of precision wouldn't just be helpful. It would be the difference between life and death, between finding a safe harbor and being lost forever in the vastness of the Atlantic. This experiment was a landmark because it moved beyond theoretical physics and into practical, real-world application. It demonstrated that the technique was not only possible but also highly reliable, even when performed by someone with relatively limited training. It proved that the basic principle using the crystal to detect the polarization pattern of skylight was a robust and effective navigational method. But the scientific inquiry didn't stop there. Other researchers have pushed the boundaries even further, testing the limits of this ancient technology. Perhaps the most dramatic extension of this research came from a team exploring whether a sunstone could be used to navigate after the sun had physically dipped below the horizon. Using a computer model based on the properties of Iceland's spar, they calculated that a skilled navigator could have located the sun's position up to 50 minutes after sunset and 40 minutes before sunrise, effectively extending the navigational day during the long twilight hours of the northern summer. This finding helps solve another Viking mystery: how they managed those incredibly long, continuous open ocean crossings without ever stopping. They weren't just sailing by day. They could have been calibrating their course by the faint, polarized glow of a sun that was, for all intents and purposes, already gone. While Iceland's spar has captured the modern imagination, it was far from the only crystal that could unlock the secrets of polarized light. The sagas speak of a solarstein, a sunstone, but they don't specify its type. This opens the door to other compelling mineral candidates, each with its own unique method of revealing the sun's path. One of the most visually striking alternatives is cordierite, a mineral more commonly known by its gemstone name, iolite. Its primary advantage lies not in splitting light, but in painting the sky with color. Iolite is a dichroic crystal, meaning it can show 2 different colors depending on the polarization of the light passing through it and its own orientation. For a Viking navigator, this would have been an incredibly intuitive tool. They would hold the stone up to a clear patch of sky, even through clouds, and slowly rotate it. As they turned it, the crystal would shift from a pale, yellowish hue to a deep, vivid violet blue. The point of the most intense, saturated blue color indicates the precise alignment with the pattern of polarized sunlight, acting like a natural compass needle pointing toward the hidden sun. This dramatic color change requires no complex interpretation of twin images. It offers a direct, visual signal that is both powerful and relatively easy to discern, even for someone with less experience. The practicality of cordierite for Viking use is also strongly supported by geography and archaeology. Significant and accessible deposits of this mineral are found throughout Scandinavia, particularly in Norway and Sweden, placing it directly within the Vikings' resource network. Furthermore, a fascinating archaeological discovery lends tangible weight to its possibility. A small, carefully worked crystal of cordierite was found among the grave goods of a 10th century Viking ship burial at Narsarsuaq in Greenland. While its purpose wasn't explicitly labeled, its presence in a maritime context, shaped by human hands, strongly suggests it was a valued object with a specific function. It's not a definitive proof, but it is a compelling piece of circumstantial evidence that the Vikings had access to and were utilizing crystals with the exact properties needed for sunstone navigation. The third contender in this ancient technological race is tourmaline, specifically the variety known as scoral. This black, opaque crystal might seem like an unlikely candidate compared to the transparent Iceland spar or the colorful iolite, but it shares a crucial property. It is also an effective polarizer. Tourmaline strongly absorbs light that is polarized in one direction while allowing light polarized in the perpendicular direction to pass through. The navigational technique would be similar to that used with the other crystals, but instead of looking for matching beams or a color shift, the user would be searching for a change in brightness. By rotating the tourmaline and viewing the sky through it, the navigator would note the orientation where the sky appears darkest, the point of maximum absorption, which is perpendicular to the direction of the sun. While this method might require a more sensitive eye for subtle changes in light intensity compared to iolite's dramatic color show, it would nonetheless provide a reliable and effective means of locating the sun's position. So, with three viable options, which crystal was the true sunstone? The answer is that there may not have been a single answer. The Viking world was vast, and their trade routes stretched across continents. It is entirely plausible, even likely, that different navigators in different regions used whatever suitable crystal was most readily available to them. A sailor from Norway might have favored a locally sourced piece of cordierite, while a Danish trader might have acquired a chunk of Iceland spar through exchange. The sunstone may well have been a functional category of tool, not a single, standardized device. What united them was not their mineral composition, but their shared ability to decipher the hidden language of light in the sky. This flexibility speaks to the Vikings' profound practicality and resourcefulness. They weren't reliant on one specific, rare technology. They understood a core natural principle and applied it using the best materials they had on hand, turning the very geology of their homeland into a key that unlocked the world. While the sagas give us the story and laboratory tests confirm the possibility, nothing speaks louder than a physical object pulled from the depths of the sea. For decades, the sunstone remained a compelling theory without a definitive artifact. That changed in 2002 with a discovery that sent ripples through the worlds of archaeology and maritime history. A team investigating a shipwreck near the island of Alderney in the English Channel unearthed something extraordinary. The wreck itself was not a Viking longship, but an English warship, the Alderney Elizabeth, which sank in 1592. This was a vessel from the late Tudor period, a time when maritime navigation was rapidly advancing with the widespread adoption of the magnetic compass and early sextants. Yet, among the standard navigational tools recovered a pair of brass dividers, a ruler, and a folding rule, lay a small, unassuming object that seemed to belong to a different era altogether. It was a rectangular block of a transparent mineral, roughly the size of a bulky bar of soap, found nestled near the other instruments. After careful analysis, researchers identified it as a crystal of calcite Iceland spar. This was not a random piece of cargo or a decorative item. Its location was the key. It was discovered in the part of the ship where the navigator would have worked, stored alongside his essential tools for charting a course across the ocean. This contextual placement strongly suggests it was a functional part of his kit, as vital to his calculations as the dividers used for measuring distances on a chart. The significance of the Alderney crystal cannot be overstated. Here was tangible archaeological proof that sailors were using calcite crystals for navigation centuries after the Viking Age, and well into the age of printed maps and magnetic compasses. This find bridges the gap between the legendary accounts of the sagas and modern scientific experimentation. It demonstrates that the knowledge of using crystals to find the sun was not lost to history after the Vikings. It was a practical, preserved technique that persisted among mariners who understood its irreplaceable value in certain conditions. A magnetic compass is useless near the magnetic poles of the far north, and it can be dangerously unreliable during violent electrical storms, when atmospheric disturbances play havoc with its needle. In these critical moments, a sunstone would have been the only reliable guide, a timeless tool born from ancient wisdom that remained relevant even as technology evolved. The Alderney crystal provides the strongest physical evidence we have because it was found in situ, in its original working context on a seafaring vessel. It moves the sunstone from the realm of theory and legend into the documented material culture of European navigation. It tells us that for some sailors, the old ways were still the best ways, and that the secret of reading the sky with a crystal was a piece of knowledge precious enough to be kept alive, passed down from one generation of mariners to the next, possibly stretching in an unbroken line all the way back to the Vikings themselves. But to view the sunstone as a standalone miracle is to misunderstand the Viking seafarer entirely. This crystal was not a magic wand. It was one sophisticated instrument in a vast and deeply mastered navigational toolkit. The Vikings were holistic navigators, true masters of their environment who synthesized information from every possible source. On the open ocean, far from any landmark, they became expert readers of the sea itself. They learned to interpret wave patterns, understanding that a subtle shift in the swell could indicate a distant landmass or an approaching weather system. The direction of the prevailing wind created a specific, recognizable pattern on the water's surface, a texture they could feel as much as see from the deck of their responsive longships. They paid close attention to the color and temperature of the water, noting how it changed near river outlets, over shallow fishing banks, or as they moved between different ocean currents. The sea spoke to them in a language of motion and hue, and they were fluent in its every dialect. The sky above offered another set of vital clues, far beyond the hidden sun. At night, when the clouds parted, they steered by the stars. The Norse had a detailed understanding of the fixed stars and constellations, using them as celestial landmarks. The North Star, Stjarna, or the guiding star, was their fixed point in the rotating heavens, providing a constant bearing for north. But their celestial knowledge was practical, not just academic. They knew which stars rose and set over specific islands or stretches of coastline, creating mental star paths to follow. This stellar navigation was complemented by a profound awareness of animal behavior. Seabirds were their aerial scouts. A lone puffin or guillemot spotted at sea might suggest land was still distant, while a flock of birds flying purposefully in one direction at dusk, returning to their nests, could be followed to shore. The Vikings observed whales and their migration routes, and even the specific types of seaweed floating past could tell them if they were in a coastal current or the deeper, open ocean. Perhaps their most crucial tool, however, was one that left no archaeological trace: a vast and meticulously preserved oral tradition. Viking navigation was an intellectual craft, passed down through generations in the form of sailing directions known as arvar. These were not simple rhymes but highly detailed mental maps, containing precise bearings, landmarks, and distances. A typical set of directions might instruct a navigator to sail a certain number of digr, a unit representing both a 12-hour sailing period and the distance covered in that time, on a specific bearing until they spotted a mountain with a distinctive double peak, then turned to follow the flight of a particular bird to a bay with a white sandy beach. This knowledge was a communal treasure, held and refined by expert navigators who could recall the precise sequence of headings, landmarks, and environmental signs for journeys spanning thousands of miles. The sunstone, then, fits into this system as a precision instrument for one specific critical task. On those days when the primary cues vanished when the stars were hidden, the birds were gone, and the sea was a uniform gray, the crystal provided the crucial data point to recalibrate their mental map. It was the tool that verified their dead reckoning, confirmed their heading, and ensured the sacred accuracy of the oral sailing directions when all other senses failed. It didn't replace their other skills. It underwrote them, providing the scientific certainty that backed up their environmental intuition and inherited wisdom. Yet for all their mastery of the sea, the most ambitious Viking voyages would have been impossible without a tool that could cut through the relentless overcast of the North Atlantic. This is where the sunstone moves from being a fascinating curiosity to a pivotal piece of historical technology, a key that may have literally unlocked new worlds. To understand its true impact, we need to overlay the crystal's capabilities onto the map of Viking expansion. Their westward journey was a leapfrog across some of the most treacherous waters on the planet, a series of incredible gambles that somehow paid off. The settlement of Iceland, beginning in the late 9th century, was a colossal undertaking. Sailing from Norway or the British Isles meant venturing over 600 miles into the open ocean, with no land in between. The journey to Greenland, first achieved by Eric the Red around 982, was an even more daunting feat. It required crossing nearly 200 miles of the Denmark Strait, a passage infamous for its brutal winds, dense fog, and drifting sea ice. And then there is Vinland, the name given to the coast of North America, which Leif Erikson reached around the year 1000. This was a voyage of staggering distance and uncertainty, pushing far beyond the known world. On these journeys, traditional coastal piloting was useless. There were no landmarks to follow, no familiar seabirds for days on end. The magnetic compass, while known in Europe by this time, was likely not used by the Vikings and would have been notoriously unreliable so close to the magnetic North Pole. For most of the voyage, their only fixed reference points were the sun by day and the stars by night. But the North Atlantic is a place of perpetual gloom, where storms can shroud the sky for a week or more. This is the precise navigational nightmare the Sunstone was designed to solve. Imagine a sturdy Viking cargo ship, heavy with settlers, livestock, and all their worldly goods, caught in a multi-day fog bank. The crew's dead reckoning their estimate of position based on speed and direction would slowly accumulate errors with each passing hour. Without a way to correct their course, they could miss their target by hundreds of miles, sailing obliviously past Greenland into the endless void of the Atlantic. A navigator with a sunstone, however, could break this cycle of uncertainty. Even through the thickest fog, he could take a reading. By finding the sun's bearing just once a day, he could provide a single, crucial fixed data point. This wasn't about getting a continuous fix on their position like modern GPS. It was about resetting the clock on their dead reckoning, That one verified bearing would allow them to correct their heading, realign their mental map with reality, and confidently continue westward. This ability to periodically correct for drift is what makes the difference between a calculated expedition and a desperate gamble. It transforms a journey from a hopeful following of bird flight paths into a repeatable, navigable route. The Sunstone didn't just help them see the sun. It provided the confidence to embark on these voyages in the first place, knowing they had a tool that could guide them through the worst conditions their gods could throw at them. It was the technological edge that turned the vast, frightening Atlantic into a highway rather than a barrier. The journey of a sunstone from a rough, unassuming mineral to a precision navigational instrument would have begun not at sea, but deep within the earth, and required a sophisticated understanding of geology and trade. Vikings were not just raiders. They were some of the most prolific and well-connected traders of the early medieval world, their networks stretching from the Silk Roads of Baghdad to the frozen shores of Greenland. This vast commercial reach was their key to sourcing the right materials. While a common mineral like calcite could be found in limestone deposits throughout Scandinavia, the exceptionally clear, high-quality Iceland spar would have been a prized commodity. The name itself is a clue, pointing to one of the most likely and abundant sources. Though the Vikings didn't settle Iceland until the late 9th century, its unique geology, dominated by volcanic activity, produces stunningly transparent calcite crystals. Once regular travel to Iceland began, this material would have become a valuable export, traded along with other Norse staples like walrus ivory, furs, and dried fish. Other candidate crystals also fit neatly into known Viking trade routes. Cordierite or iolite forms in metamorphic rocks and is found in Norway and Sweden, putting it directly within their sphere of control. A navigator from a Norwegian fjord might have simply needed to consult a local stoneworker or travel inland to acquire a suitable piece. Tourmaline, while less common, could have been obtained through trade with peoples to the east, moving along the river systems that connected the Baltic to the Byzantine and Arab worlds. The Vikings were masterful opportunists, always on the lookout for valuable resources. A unique, clear crystal with strange optical properties would not have been overlooked. It would have been recognized for its potential utility and value, collected, traded, and eventually experimented with by those who spent their lives reading the environment. Once a suitable raw crystal was acquired, the real craft began. A freshly quarried piece of calcite or cordierite is not a ready-made tool. It must be carefully shaped to be both functional and durable. The Vikings were skilled lapidaries, experts in working stone for everything from intricate beads and pendants to sharpening whetstones and weighty loom weights. The process of crafting a sunstone would have drawn directly on these well-established skills. The first step would be to assess the raw mineral and cleave it. Crystals like calcite have a perfect cleavage, meaning they break along defined, flat planes when struck correctly. An experienced craftsperson would have used a small hammer and a sharp, hard point perhaps made of iron or another stone, to tap the crystal precisely along its natural cleavage lines, splitting it to create a flat, smooth face that was optimally transparent and free of internal flaws. After cleaving, the stone would need to be ground and polished to its final form. This was likely done using a technique called lapidary, where the crystal is rubbed against a coarse abrasive stone, such as sandstone, with water or sand acting as an additional grinding agent. Through patient, meticulous effort, the sharp edges would be smoothed down, and the faces would be polished to a high clarity. The goal wasn't to create a perfect geometric shape, but a functional one, a piece that was comfortable to hold, stable enough not to roll on a heaving deck, and with at least one pair of parallel, transparent faces to allow light to pass through cleanly for an accurate reading. The final product might have been a palm-sized, rectangular block or a more ergonomic, rounded pebble shape, polished smooth from hours of handling. Some may have even been drilled or set in a simple wooden frame to make them easier to hold and rotate steadily against the sky, though no such artifacts have been found to confirm this. Maintaining these delicate instruments in the harsh marine environment would have been a constant concern. A crystal scratched by sand or chipped by a fall onto the ship's deck could become useless, its optical properties compromised. We can imagine a navigator storing his sunstone in a protective pouch made of soft leather or felt, keeping it separate from metal tools and other abrasive objects. It would have been one of his most valued possessions, cared for with the same reverence a modern sailor has for a sensitive sextant. Its performance would also need to be verified. A simple test would have been to use the stone on a clear day to confirm it could accurately locate a sun that was already visible, ensuring the tool was still functioning correctly before trusting it in a crisis. This process from sourcing the raw mineral through to the skilled crafting and diligent maintenance shows that the sunstone was far more than a lucky rock. It was a purpose-built scientific instrument, born from a culture that possessed not only daring and seamanship, but also a deep and practical mastery of the natural world. Despite the compelling evidence, a healthy dose of skepticism is not just warranted but essential for a complete historical picture. The sunstone theory, while elegant and scientifically plausible, is not without its significant challenges and vocal critics within academic circles. The primary and most substantial hurdle is the stark lack of direct, irrefutable archaeological evidence from a confirmed Viking context. To date, not a single crystal has been recovered from a Viking Age grave or settlement site with an unambiguous label identifying it as a navigational tool. The cordierite piece from the Greenland burial is a tantalizing clue, but its purpose remains interpretative. It could have been a jeweler's raw material, a decorative object, or even a talisman with spiritual significance rather than a scientific instrument. The Alderney find is powerful, but it comes from a ship centuries removed from the Viking era, proving the practice existed later, but not conclusively proving its origin with the Norse. Some historians and archaeologists argue that the sagas, our main textual source, are being overinterpreted. These stories are complex literary works, layered with Christian morality tales, political propaganda, and mythological symbolism. Could the sunstone be more of a literary device than a historical one? In the context of the sagas, the characters who use the sunstone are often portrayed as particularly wise or cunning, sometimes even possessing almost magical foresight. The stone could therefore be a narrative symbol, a physical object that represents their superhuman intelligence and connection to the old ways, especially in stories written by Christians remembering a pagan past. It serves as a convenient plot device to demonstrate a character's skill, much like a detective in a story always finding the one clue everyone else missed. Another point of contention is the question of necessity and widespread use. Critics point out that the Vikings successfully colonized Iceland and reached Greenland before the dates of the saga, accounts that mention the sunstone. This suggests that while the crystal might have been a helpful innovation, it was not a prerequisite for their most famous voyages. The core of Viking navigation was, and always would have been, their immense, accumulated environmental knowledge and oral tradition. Furthermore, mastering the use of a sunstone requires a specific understanding of optical principles that, while demonstrable, is not intuitive. Could this skill have been common enough among sailors to be a standard part of their practice? Or was it a specialized trick known only to a few elite navigators? The sagas themselves only mention it a handful of times, which could indicate it was a rare technique, not a commonplace tool. Alternative theories also exist to explain the Vikings' feats without relying on a single, magical-seeming crystal. One compelling idea is that they used a different kind of bearing dial, a primitive but effective sun compass. A wooden disc with a central gnomon or pin could cast a shadow that indicates the sun's direction. A fragment of such a device, with what appear to be navigational markings, was found at a Viking Age site in Greenland. While useless on an overcast day, it would have been highly effective when the sun was visible. Another theory suggests they relied heavily on what we now call polarimetric vision, the innate, though usually subconscious, human ability to detect the pattern of polarized light in the sky. Some people, often with practice, can perceive a faint hourglass-shaped pattern known as Heidinger's brushes in their field of vision when looking at a polarized blue sky. It's a subtle effect, but it's possible Viking navigators trained themselves to see this pattern and use it to locate the sun without any tool at all, making the sunstone merely a technological aid to enhance a natural human ability they had already honed to a fine edge. The debate ultimately may never be settled with absolute certainty. The sunstone exists in a historical gray area, a theory that fits the facts beautifully but lacks the single, smoking gun artifact that would silence all doubt. Perhaps the truth lies, as it often does, in a synthesis of these perspectives. The sunstone likely was a real tool, but not a ubiquitous one. It may have been a specialized instrument used by expert navigators on the most dangerous open ocean passages, a secret weapon pulled out only when every other method failed. Its infrequent mention in the sagas could reflect its actual rare and precious nature. It wasn't a symbol of magic, but a tool of last resort, a crystal lens that turned the invisible into the visible and provided a thread of certainty in a world of fog and chaos. This view allows us to accept the scientific validation and the later archaeological evidence from Alderney without having to rewrite the entire history of Viking navigation. It positions the sunstone not as the sole key to their success, but as one brilliant innovation in a vast and sophisticated system of wayfinding, a testament to their practicality and their relentless drive to find an advantage against the sea. To truly appreciate the Viking achievement, we need to widen our view and see them not in isolation, but as one thread in a rich global tapestry of ancient navigation. Across the world, other cultures were also mastering the art of wayfinding, each developing a unique set of tools perfectly adapted to their environment and ambitions. By placing the Vikings alongside the Polynesian wayfinders, the Arab traders, and the Mediterranean sailors, the distinctiveness of their approach and the special role of the sunstone comes into sharper focus. Far across the world, in the vast expanse of the Pacific Ocean, Polynesian navigators were undertaking voyages that dwarfed even the most ambitious Norse journeys. Sailing vast double-hulled canoes called waka, they settled islands scattered across millions of square miles of open water, from Hawaii to New Zealand to Easter Island. Their system, which we now call wayfinding, was a holistic and deeply spiritual art form that shared the Vikings' profound connection to the natural world, yet operated on entirely different principles. Without any instruments at all, wayfinders relied on an encyclopedic knowledge of the stars, using them not as a compass but as a star path. They memorized the precise point on the horizon where specific stars would rise and set, creating a mental star compass that provided unwavering bearings. They read the ocean itself as a text, interpreting the subtle patterns of swells refracted around distant islands, the specific species of birds and their flight directions at dusk, and even the color and temperature of the water. A key tool was the perception of cloud formations. The unique shape and color of clouds often gathered over an island, betraying its location long before it was visible. This method was deeply intuitive and required a lifetime of training, passed down through generations. Unlike the Vikings, who may have used a physical object like the sunstone to obtain a precise data point, the Polynesian wayfinder's body and senses were the instrument, a perfect fusion of human and environment. Meanwhile, in the deserts and seas of the Middle East, Arab traders were pioneering a form of navigation that was highly mathematical and instrument-based, laying the groundwork for modern cartography. Their world was defined by the trade routes of the Indian Ocean and the deserts of the Silk Road, demanding a different kind of precision. While they certainly possessed deep environmental knowledge, their great innovation was the development of the camel, a simple but brilliant rectangular plate attached to a string with a series of knots. The navigator would hold the camel at arm's length, aligning its top and bottom with the horizon and a specific star, usually Polaris. The knot held between the teeth indicated the latitude, allowing for remarkably accurate sailing along a parallel. This was a quantifiable, repeatable measurement. Arab sailors also produced incredibly detailed navigational texts called ramangs and detailed portolan charts, which focused on coastlines, harbors, and compass bearings. Their approach was systematic, documented, and relied on instruments that provided numerical data. The Viking method, by contrast, was more integrated with oral tradition and environmental cues, using the sunstone not for a numerical fix, but to confirm a directional bearing within their mental map of sailing routes. In the relatively confined and well-charted waters of the Mediterranean, classical and later sailors like the Greeks, Romans, and Byzantines employed a method known as cabotage, or coastal piloting. Their primary goal was to keep land in sight whenever possible, sailing from headland to headland. When they did venture out of sight of land, they relied on lead lines to measure depth and take samples of the seabed, knowing whether you were sailing over sand, mud, or shingle could tell you exactly where you were on a well-traveled route. They also used detailed periplus documents, which were written sailing directions describing coastlines, landmarks, and safe harbors in sequence, much like the Viking Orvar but committed to parchment. The development of the magnetic compass in the medieval period revolutionized their navigation, but it was a tool for the well-mapped, bustling Mediterranean, not the trackless gray wastes of the North Atlantic. So what made the Viking approach, and the sunstone by extension, so unique? It was a product of their specific, brutal environment. The North Atlantic offered none of the predictable star paths of the Pacific tropics, none of the calm, confined waters of the Mediterranean, and none of the well-documented trade winds of the Indian Ocean. It offered instead fog, cloud, storm, and a low-hanging sun that could vanish for days. The Vikings synthesized elements from all these systems: the environmental awareness of the Polynesians, the directional precision sought by the Arabs, and the detailed oral sailing directions of the Mediterranean, but they forged them into a system for surviving the impossible. The sunstone was the technological embodiment of this adaptation. It was a tool for the worst conditions, a way to extract a single, crucial piece of data from a seemingly featureless void when every other method had failed. It wasn't about elegant star paths or mathematical latitude. It was about raw, pragmatic survival. It provided the confidence to sail into the gray, to trust that even when the world dissolved into mist and water, they could still find their way. This unique combination of holistic environmental knowledge and a specific physics-based tool is what sets them apart, a testament to their ingenuity in the face of one of the most demanding seascapes on Earth. Yet even the most brilliant technology can be eclipsed by the relentless march of progress. The Sunstone, for all its sophistication, did not remain the navigator's premier tool forever. Its gradual fade from maritime use was not a sudden disappearance, but a slow surrender to a wave of new inventions and changing seafaring landscapes that transformed European navigation in the late medieval period. The most formidable challenger to arrive on the scene was the magnetic compass. This simple yet revolutionary device, which likely entered European awareness through trade with the Arab world and China around the 12th century, offered something the sunstone could not: constant, uninterrupted guidance. A compass needle points north regardless of the weather, be it fog, rain, or the dead of night. It provides a fixed reference that requires no interpretation of light patterns or clear patches of sky. For sailors plying the increasingly busy trade routes of the Mediterranean and the European Atlantic coast, this reliability was invaluable. It allowed for more precise charting, the creation of standardized portolan maps with detailed compass roses, and a democratization of navigation. Using a compass required less of the specialized, experiential knowledge needed to master a sunstone. Almost any crew member could learn to follow a bearing. The sunstone, in contrast, was a specialist's tool for the worst moments, while the compass was an everman's tool for every moment. This technological shift was accompanied by a parallel revolution in astronomical knowledge. The Viking method of navigation was deeply empirical, born from generations of observation and oral tradition. But the late medieval and Renaissance periods saw the formalization of celestial navigation into a mathematical science. The development of instruments like the cross-staff, and later the backstaff and mariner's astrolabe, allowed sailors to measure the angle of the sun or stars above the horizon to calculate their latitude with increasing accuracy. This provided a numerical fix on their position, a coordinate on the growing grid of the known world. This scientific approach, combined with the compilation of detailed astronomical tables and almanacs, moved navigation from an art form passed down through spoken sagas to a technical skill that could be learned from books. The sunstone's function, to find the sun's azimuth or horizontal direction, was made redundant by a compass for bearing and a cross-staff for altitude, a combination that offered far more navigational data. Perhaps the most significant factor in the sunstone's decline was a fundamental change in where and how Europeans sailed. The Viking world was the open North Atlantic, a realm of overcast skies and high latitudes where the magnetic compass could behave erratically. But as the economic center of Maritime, gravity shifted south to the Mediterranean and the spice routes of the Atlantic islands. Sailors operated in latitudes where the sun was more frequently visible, and the magnetic poles posed less of an issue. The ships themselves changed, becoming larger, heavier carracks and caravels designed for carrying bulk cargo over long distances. These vessels were less agile and responsive to the subtle cues of wave and wind that the Vikings relied upon. Their captains depended more on charts, instruments, and dead reckoning logged in a ship's journal. The holistic, environmentally attuned Viking system, with the sunstone as its precision corrective, was less suited to this new era of commerce-driven, instrument-reliant exploration. The sunstone became a relic of a specific time and place, a tool for a particular kind of ocean and a particular kind of sailor that was slowly fading into history. For centuries after the Viking Age, the sunstone faded into the realm of myth, a curious footnote in the sagas that modern historians often dismissed as pure legend. The very idea that medieval sailors could harness the properties of polarized light seemed anachronistic, a fanciful story rather than a historical reality. The turning point came in the mid-20th century, not from a new archaeological dig, but from the curiosity of a single Danish science teacher and amateur archaeologist named Thorkild Ramsku. In the 1960s, Ramsku began to seriously ponder the Old Norse texts. He was fascinated by the specific, almost technical descriptions of the sunstone's use, and became convinced they pointed to a real method based on natural principles. He proposed a radical idea, that the solar stein was a crystal that functioned as a polarizer, allowing a navigator to detect the sun's position through its interaction with the polarized light of the sky. His initial hypotheses, published in popular science articles and later in his 1967 book, challenged the academic status quo and laid the groundwork for a completely new field of experimental historical research. While his ideas were met with skepticism at first, he had planted a seed, transforming the sunstone from a fairy tale into a solvable scientific puzzle. Ramsku's theories needed more than historical argument. They required rigorous physical proof. This is where modern optical physics entered the story, providing the tools to test a 1,000-year-old idea. The key was understanding skylight polarization. Scientists had long known that sunlight scattering through Earth's atmosphere creates a predictable pattern of polarized light, with the vibration direction of the light waves forming concentric circles around the sun. This pattern is strongest at a 90-degree angle from the sun and remains detectable even under a uniform overcast sky, as clouds only partially scatter the light without completely randomizing its polarization. This was the invisible map Ramsku believed the Vikings were reading. Researchers began testing various crystals mentioned in the sagas to see if they could reliably decode this map. Iceland's spar, with its dramatic double refraction, proved particularly effective. The method was simple yet powerful. By rotating the crystal and observing the point where the two split images achieved equal intensity, a user could pinpoint the sun's azimuth with remarkable accuracy. The most compelling validations emerged from controlled field experiments. A landmark study led by Gabor Horvath in 2011 put the Iceland spar theory to the test under real-world overcast conditions. Participants were asked to use a calcite crystal to estimate the sun's position, and their results were compared to the actual solar coordinates. The findings were stunning. The error margin was consistently less than 1 degree, a level of precision more than sufficient for ocean navigation. This wasn't just a laboratory trick. It was a demonstrably viable technique. Further research pushed the boundaries even further. A team from the University of Rennes in France conducted a fascinating study in 2011, using a computer model to demonstrate that a sunstone could theoretically be used to locate the sun even after it had dipped below the horizon, leveraging the lingering polarization in the twilight sky. This suggested Viking navigators could have extended their celestial sight well beyond sunrise and sunset, gaining precious extra hours of guidance during the long summer nights of the Arctic. This scientific resurrection of the sunstone is a powerful example of how interdisciplinary collaboration can solve historical mysteries. Physicists provided the principles, archaeologists provided the context, and experimentalists bridged the gap with practical testing. The journey from Ramscu's speculative articles to peer-reviewed papers in optical journals illustrates a profound shift in our perception of the past. We are no longer just interpreting texts. We are recreating ancient technologies to see if they hold up under modern scrutiny. The Sunstones validation does more than just explain how the Vikings might have navigated. It fundamentally changes how we view them. It reveals a culture not of superstitious barbarians, but of astute observers of the natural world, brilliant practical scientists who learn to read the subtle language of light written across the sky. They turned a piece of the earth into a sophisticated optical instrument, and thanks to a few curious modern minds, we are now able to finally understand and appreciate their ingenious invention. While the laboratory results were compelling, the ultimate test for the sunstone theory would take place not in a controlled setting, but out on the open ocean, facing the same raw elements the Vikings conquered. In recent decades, a series of ambitious modern expeditions have aimed to do just that, to strap on a Viking tunic, pick up a replica sunstone, and sail the old routes using only the tools and methods available 1,000 years ago. These voyages are more than just adventurous reenactments. They are rigorous experiments in experimental archaeology, putting centuries-old theories to the ultimate, unforgiving test. One of the most prominent of these endeavors was the 1996 voyage of the saga Sigler, a reconstructed Viking nar. While its primary mission wasn't solely sunstone navigation, the crew relied extensively on traditional Norse methods, including dead reckoning and celestial observation. Their successful journey from Norway to Iceland, and then onward to Greenland and North America, demonstrated the astonishing feasibility of Viking seamanship. However, they also encountered the very problem the sunstone was designed to solve: prolonged periods of overcast weather that completely obscured the sun and stars for days on end. Without a modern compass as a backup, they reported that maintaining an accurate course during these stretches was incredibly difficult, leading to significant navigational uncertainty. Their experience powerfully illustrated why a tool like the sunstone wouldn't just be helpful. It would be absolutely critical for maintaining morale and course accuracy during a transatlantic crossing. A more focused test took place in 2007, when a team of researchers and sailors embarked on a 3-week journey aboard the Havhingsten fra Glendalough, the sea stallion from Glendalough, a precise reconstruction of a large Viking warship. During their sail from Denmark to Ireland, they actively experimented with a cordierite sunstone. Their findings were a fascinating mix of triumph and reality. On days with high, thin cloud cover, the sunstone performed admirably, allowing them to determine the sun's position with a consistency that surprised even the skeptics aboard. The color shifts in the iolite crystal were clearly visible and could be correlated with the sun's hidden path. However, they also ran into significant practical challenges. On days with heavy, low-lying fog and thick, uniform cloud cover, the polarized light pattern became too weak and diffuse for the human eye to detect any meaningful change to the crystal. Furthermore, using the small, smooth stone on a pitching deck in a stiff wind proved to be a delicate operation requiring a steady hand and a great deal of patience. Perhaps the most definitive modern demonstration came from a land-based but highly realistic experiment conducted by the Royal Institute of Navigation in the United Kingdom. They placed a test subject in a closed environment driving simulator that was programmed to replicate the pitching and rolling motion of a Viking longship at sea. The participant was then given a crystal of Iceland spar and tasked with taking a series of bearings under simulated overcast skies. The results were telling. While the subject could eventually determine the correct bearing, the motion of the ship significantly increased the time required to get an accurate reading and introduced a larger margin of error. This experiment highlighted a crucial aspect of Viking navigation that is often overlooked: the immense skill and practiced calm of the navigator himself. It wasn't enough to just have the tool. One needed to be an expert in its use, able to block out the physical discomfort and terror of a stormy sea to execute a precise, delicate optical procedure. This suggests that sunstone navigation was likely a specialized skill, reserved for the most experienced and steady-handed individuals on the ship, not a common practice everyone could perform. These modern voyages have collectively moved the sunstone from the realm of intriguing theory into the domain of practical, though challenging, historical practice. They confirm that the technique works with enough reliability to be a viable navigational aid, but they also paint a clearer picture of its limitations. The sunstone was not an infallible magic crystal. It was a precision instrument that functioned best under certain conditions and required a skilled operator. Its true power was likely as part of a suite of techniques. A navigator might use the stone to get a bearing during a break in the clouds, use that to correct his dead reckoning, and then rely on wave patterns and bird behavior to maintain that course until he could get another fix. These modern adventurers have not proven conclusively that the Vikings used sunstones, but they have proven beyond a doubt that they could have. They have given us a visceral, experiential understanding of what it might have felt like to hold that crystal up to a gray sky, searching for a glimpse of the hidden sun, and feeling the profound relief when its invisible position finally revealed itself, offering a thread of certainty in an endless sea of doubt. This captivating blend of history and mystery has made the sunstone an irresistible subject for modern storytellers, allowing it to sail far beyond academic journals and into the heart of popular culture. Documentaries have been particularly instrumental in bringing the theory to a mass audience, often using a powerful combination of dramatic reenactments and cutting-edge science to make the case. Productions from major networks like the BBC and National Geographic frequently feature segments on Viking navigation, using computer-generated imagery to visualize the invisible, animating the polarization patterns in the sky and the splitting of light within a calcite crystal in a way that pure explanation never could. These visualizations transform an abstract scientific principle into a tangible, almost magical process, allowing viewers to feel as if they are peering through the navigator's eyes. While these programs generally strive for accuracy, the need for compelling television can sometimes lead to a slight sensationalism, perhaps overstating the certainty of the theory or presenting it as the sole, definitive key to Viking success, rather than one sophisticated tool among many. The overall effect, however, is overwhelmingly positive, sparking curiosity and wonder in millions of viewers who might never have encountered this fascinating historical puzzle otherwise. The allure of the sunstone has proven equally potent in the realm of literature, where authors of historical fiction and fantasy have seized upon its poetic potential. In novels, the sunstone often transcends its probable historical role as a practical tool and becomes a symbol of ancient wisdom, a coveted artifact imbued with almost mystical significance. A fictional navigator might be a keeper of a sacred, secret knowledge, using the stone for purposes that stretch beyond mere wayfinding, perhaps to perform rituals, make prophecies, or communicate with the gods. This literary license is a testament to the power of the idea, The concept of a crystal that reveals hidden truths is a narrative device as old as storytelling itself. While these portrayals take creative liberties, they often get the fundamental premise right, that the stone worked by interacting with light in a special way. They introduce the concept to readers who then might be inspired to investigate the real history behind the fiction, creating a valuable gateway to a deeper understanding. Perhaps the most interactive and engaging modern exploration of the Sunstone occurs in the world of video games, where players don't just learn about history, they actively participate in it. The blockbuster game Assassin's Creed Valhalla, set during the Viking invasion of England, features the Sunstone as a collectible item and integrates its use into gameplay mechanics. Players can literally equip the crystal and use it to solve environmental puzzles, rotating it on their screen to align beams of light and reveal hidden paths or secrets. This is a brilliant example of gamified learning. It takes the core scientific principle of detecting light polarization and translates it into a hands-on, intuitive action. While the game takes its expected creative freedoms with history, the very inclusion of the Sunstone acknowledges its place in the popular conception of the Viking Age and introduces a new, global generation to the concept. It transforms players from passive observers into active navigators, if only in a digital world, fostering a unique and memorable connection to this ancient technology. The journey of the Sunstone from obscure saga reference to featured plot device highlights a fascinating cultural process, how a fragment of history can be polished and reshaped by each generation to reflect its own values and fascinations. In our modern, technology-saturated world, the idea that ancient people could harness the laws of physics with a simple crystal is deeply appealing. It resonates with a growing desire to rediscover lost wisdom and to see past societies not as primitive, but as ingenious and resourceful. The Sunstone in popular culture becomes a symbol of that ingenuity. It represents a harmonious relationship with nature, a time when cutting-edge technology was not based on silicon and code, but on a deep, observant understanding of the natural world. Whether it's presented with scientific rigor in a documentary or with mythic grandeur in a fantasy novel, its continued presence in our stories ensures that the legacy of Viking exploration and the enduring human thirst for discovery remains alive and vibrant, inspiring us to keep looking for hidden patterns in the world around us. Yet for all its potential, the Sunstone was far from an infallible magic solution. Its effectiveness was tightly bound by the very environment it was designed to conquer, presenting navigators with a set of formidable practical challenges. The most significant limitation was the nature of light itself. While the theory of detecting polarized skylight through cloud cover is sound, its application hinges on the type and thickness of the clouds. On days with high, thin cirrus clouds, plenty of polarized light still filters through, making the crystal an effective tool. However, under a dense, low-lying blanket of nimbostratus clouds, the kind that brings continuous rain or snow, the situation changes dramatically. These thick, multi-layered clouds act like a diffuse filter, scattering the incoming sunlight so many times that its original polarization pattern becomes almost completely scrambled. In these conditions of truly zero visibility, where the world dissolves into a uniform gray murk, even the most sensitive sunstone would have struggled to find a clear signal. The navigator might rotate the crystal endlessly, searching for a change in brightness or color that simply wasn't there, leaving him no better off than if he had relied on dead reckoning alone. Mastering this delicate instrument demanded a rare and highly specialized skill set that went far beyond simple seamanship. Using a sunstone effectively was not like reading a compass. It was a nuanced art form that required a deep, almost intuitive understanding of optics, weather patterns, and human physiology. The navigator needed a supremely steady hand and an immense amount of patience, especially on the pitching deck of a longship in heavy seas. He had to isolate a patch of sky, hold the crystal rock steady before his eye, and rotate it with minute precision, all while his world was heaving violently beneath him. This required years of practice to develop the necessary muscle memory and concentration. Furthermore, interpreting the results was highly subjective. With an Iceland spar crystal, was the intensity of the two beams truly equal, or was one just slightly brighter? With a cordierite stone, was that the deepest possible blue, or just a dark shade of gray? These subtle distinctions could mean a difference of several degrees in bearing, a small error that would compound over hundreds of miles into a catastrophic miss. This high skill ceiling suggests that sunstone navigation was likely not a common practice among the entire crew, but rather a guarded specialty of a single, highly trained individual. The navigator whose knowledge and steady nerve were as valuable as the ship itself. There were also specific situations where relying on a sunstone would have been actively inferior to other, more reliable methods in the Viking repertoire. Under a clear night sky, for instance, steering by the stars would have been infinitely more straightforward and accurate. The fixed rotation of the constellations provided a constant and easily readable celestial clock and compass, requiring no special tools or interpretation. Similarly, when within sight of land or in familiar coastal waters, the old-fashioned techniques of piloting were far more effective. Reading the shape of the coastline, recognizing specific rock formations, monitoring water depth with a lead line, and observing the behavior of local wildlife provided a wealth of immediate, unambiguous data that no crystal could match. The sunstone's specific niche was that narrow, terrifying window of time during a multi-day open ocean crossing when the ship was far from any landmark and the sky was completely overcast, but not so thickly clouded as to obliterate all polarized light. It was a tool for a very specific crisis, not for everyday sailing. This reality check helps us refine our image of the Viking navigator. He was not a wizard who could conjure the sun from nothingness, but a pragmatic problem solver with a deep bag of tricks. His genius lay in knowing precisely which tool to use and when. The sunstone was his precision instrument for a specific set of difficult conditions, a valuable option to break a deadlock when his primary methods failed. It was the technological equivalent of a spare rudder not used on every voyage, but absolutely vital to have on board when disaster struck. Its true power was not as a standalone miracle device, but as one critical component in a vast, sophisticated, and resilient system of wayfinding that allowed the Vikings to stare into the gray abyss and sail forward with confidence. Despite the compelling narrative that has been built around the Sunstone, its place in history is far from settled, resting at the center of ongoing and often fierce academic debate. The controversies are not merely about minor details. They strike at the very heart of the theory, challenging the interpretation of the sagas, the dating of key artifacts, and the very function of the objects we point to as evidence. To fully understand the Sunstone is to engage with these disputes, where every piece of evidence is scrutinized and every conclusion is contested. The most fundamental battleground is the interpretation of the old Norse sagas themselves. While proponents see the matter-of-fact descriptions of the Sunstone as proof of its common use, Skeptics argue that these texts are being read with a modern, overly literal eye. The sagas are not straightforward historical records. They are literary works composed centuries after the events they describe, often with clear political, religious, or symbolic agendas. In the context of these stories, the characters who use the sunstone are often portrayed as exceptionally wise or clever, sometimes possessing an almost supernatural foresight. Critics, therefore, propose that the solarstein might be less a description of a real tool and more a narrative device, a physical symbol used by Christian authors to represent the intelligence and pagan-era ingenuity of their ancestors. It serves as a convenient plot mechanism to demonstrate a character's unique skill, much like a magical object in a fantasy tale, rather than a detailed manual on Viking navigation techniques. This literary perspective forces us to ask whether we are seeing a historical reality or a powerful piece of storytelling that has been mistaken for one. The archaeological evidence, often hailed as the smoking gun, is itself shrouded in controversy. The discovery of the Alderney crystal was a watershed moment, but its interpretation is hotly disputed. The primary criticism lies in its context and dating. The shipwreck is from 1592, a full 6 centuries after the end of the Viking Age. While it proves that someone was using a calcite crystal for navigation in the late 16th century, it does not conclusively prove that the Vikings did. It is entirely possible that the technique was a later innovation, developed in the medieval or early modern period, and then mistakenly projected backwards onto the Vikings by over-eager historians. Furthermore, some archaeologists question whether the crystal was truly a navigational instrument at all. Could it have had another purpose? In the 16th century, calcite crystals were used in a variety of ways, including in the early optical experiments that would lead to the invention of the microscope. It might have been a curiosity, a raw material for a craftsman, or even a weight for a fishing line. Its placement near navigational tools is suggestive, but not definitive proof of its function. Without an explicit inscription or a Viking-era parallel, the link remains circumstantial. The cordierite crystal found in the Greenland Norse settlement faces similar skepticism. While its presence is intriguing, there is no marking or specific context that labels it a navigational aid. The Norse were skilled lapidaries who worked with a variety of stones for jewelry, tools, and trade. This specific piece could have been intended for a bead, an inlay for a decorative object, or simply a valued raw material gathered for its color. Without finding a crystal securely nestled next to a steering oar or within a navigator's personal kit in a Viking grave, the evidence remains tantalizingly ambiguous. The absence of such a clear, contextual find from the core Viking age is a silence that critics find deafening. If the sunstone was so vital to their most ambitious voyages, why have we not found a single unequivocal example in any of the thousands of excavated Viking graves, many of which contain the tools of their owner's trade? These debates are fueled by a broader philosophical divide in archaeology and history between what we might call maximalist and minimalist interpretations. Maximalists are willing to connect dots, using scientific plausibility and later analogies like the Alderney find to build a convincing, though not perfectly proven, case for Viking innovation. Minimalists demand direct, incontrovertible proof and warn against the romanticization of the past, arguing that we must strictly limit our claims to what the evidence can undeniably support. In the case of the sunstone, the maximalist view gives us a brilliant, compelling story of ancient scientific achievement. The minimalist view cautions that we may be creating a beautiful myth, grafting a later technology onto a past culture we admire, because the idea of Vikings harnessing the physics of light is more appealing than the simpler reality of their incredible, but entirely traditional seamanship. This tension is not a weakness in the field, but its greatest strength, ensuring that every theory is rigorously tested and that our understanding of the past remains dynamic, contested, and alive. To truly grasp the Sunstone's place in the Viking world, we must look beyond its function as a mere instrument and see it as an object woven into the very fabric of their beliefs. For the Norse, the sun was not just a celestial body, it was a divine force, a life-giver, and a central player in their cosmic drama. They knew it as Sol, a goddess driving her chariot across the sky, perpetually pursued by the wolf's girl. Each day was a victory, each sunset a moment of terror that she might be caught, plunging the world into eternal darkness. This mythology wasn't just a story, it was a framework for understanding their existence in a harsh and often sun-starved environment. In this context, a tool that could reveal the sun's hidden presence would have been imbued with profound symbolic power, a literal touchstone to the divine. It wasn't just finding a bearing, it was confirming that the gods were still there, that Sol had once again eluded the wolf, and that order was maintained in the cosmos. This connection transforms the Sunstone from a clever piece of technology into a potential sacred object, a talisman of hope and reassurance. Imagine the psychological impact on a crew lost in a weeks-long North Atlantic gale. Morale would be crumbling, fear would be a palpable force, and whispers of divine abandonment would be as dangerous as the waves themselves. In this moment of crisis, the navigator doesn't just pull out a tool, he performs a ritual. He holds up the crystal, a piece of the earth that holds a secret conversation with the heavens. The slow, deliberate rotation is a search not just for light, but for a sign. And when the crystal aligns, when it reveals the path of the hidden sun, it does more than provide a direction to steer. It delivers a spiritual revelation. It is a physical manifestation of faith, proving that even when the gods are invisible, their presence and their favor remain. The sunstone, in this light, becomes a priestly implement, and the navigator becomes a mediator between the crew and the divine, wielding a form of magic that was all the more potent because it was real. This intertwining of the practical and the spiritual was a hallmark of Norse culture. Their world was not divided into separate boxes of science and religion. Every aspect of life was infused with sacred meaning. A skilled blacksmith was seen as possessing not just technical knowledge, but also a touch of magical prowess, channeling the power of the earth ore and fire to create objects of power. Similarly, a navigator or leithsögumaður pathfinding man was more than a technician. He was a master of mysteries, a reader of omens in birds and waves, and a keeper of the oral maps that were their most valuable commodity. His ability to use the sunstone would have been viewed as a special wisdom, a gift that set him apart. It's plausible that certain crystals were considered more potent than others, perhaps blessed in a ceremony or passed down through generations within a family of renowned sailors, accumulating a legacy of successful voyages and near-miraculous rescues. The stone itself could have been seen as having a spirit or a will, a hamingja or luck that favored its owner. We can also find echoes of the sunstone's symbolic function in other Norse artifacts, particularly those associated with seafaring and authority. The Viking Age weathervane, often an ornate, gilded iron plate found on high-status ships, was a practical tool for showing wind direction, but its elaborate decoration, frequently featuring animal interlace and possibly imagery of the sun, suggests it also served as a protective totem, dedicated to ensuring favorable winds from the gods. A captain's scepter or a ceremonial axe might feature sun wheel symbols or depictions of Sol. In this company, a sunstone fits perfectly. It would be the navigator's equivalent of a king's sword, a functional object of power that also carried immense symbolic weight, representing his authority, his connection to the divine, and his responsibility for the lives of everyone on board. It was a key that unlocked both a physical direction and a psychological state of certainty, making it one of the most potent and multi-layered tools ever developed in the ancient world. This ancient art of reading the sky is not just a subject for history books. It's a living skill being reawakened in workshops and on the decks of replica longships around the world. Cultural organizations and dedicated enthusiasts are leading a fascinating movement to revive these traditional wayfinding methods, ensuring the navigator's profound connection to the environment is passed on rather than lost to time. In places like Denmark, Norway, and Iceland, you can now find hands-on courses where instructors guide students through the precise technique of using a calcite or cordierite crystal. The learning process is a powerful blend of science and sensory awareness, teaching participants to quiet their minds and focus on the most subtle visual clues. They learn to hold the stone steady, to rotate it with patient increments, and to interpret the faint shifts in light that our modern eyes are usually too distracted to notice. It's a practice that demands and cultivates a deep sense of presence, pulling you completely into the moment and connecting you to a 1,000-year-old legacy of observation. Museums have become crucial hubs for this educational revival, moving beyond static displays to create truly immersive experiences. The Viking Ship Museum in Roskilde, Denmark, for instance, doesn't just show you a preserved longship. It offers sailing trips on reconstructed vessels where the theory of sunstone navigation is put into practice right out on the fjord. Visitors can stand beside a trained navigator, feel the wind, and watch as the crystal is held up to a cloudy sky, making the invisible suddenly tangible. Interactive exhibits use light boxes and special filters to simulate polarized skylight, allowing people to try aligning the stone themselves in a controlled environment before braving the elements. This approach transforms abstract concepts into something you can see and do, demystifying the science while simultaneously deepening the appreciation for the Viking achievement. It shifts the sunstone from a mythical object behind glass into an understood and functional tool. The push to preserve these skills is driven by a powerful desire to safeguard intangible cultural heritage, the knowledge and traditions that are just as important as any physical artifact. For Nordic communities, this is a way of reconnecting with a foundational part of their identity, celebrating the ingenuity of their ancestors not as a primitive people, but as brilliant innovators. This isn't about rejecting modern technology. It's about understanding the roots of exploration and fostering a profound respect for the natural world that our GPS-dependent society often overlooks. By learning to navigate by the sun, the stars, and the waves, students gain a visceral understanding of their place in the environment, developing a literacy of the natural world that is increasingly rare. This revival ensures that the Sunstone story continues to be told not as a concluded mystery, but as an ongoing conversation between the past and the present, inspiring a new generation to look at the sky and see not just weather, but a map waiting to be read. Despite all we've learned, the Sunstone remains one of history's most captivating cold cases, with its final verdict still pending. The most pressing question hanging over researchers is a simple one of archaeology. Will we ever find a sunstone in a definitive Viking context? The discovery of a calcite or cordierite crystal within the personal effects of a navigator buried with his ship would be the ultimate smoking gun, instantly transforming the theory into established fact. Until then, every argument, no matter how scientifically sound, must contend with that evidential silence. The search continues, with archaeologists increasingly employing advanced technologies like ground-penetrating radar to explore known Viking sites without disturbing them, hoping to identify promising targets for future excavation that might finally yield this elusive artifact. Beyond the hunt for the object itself, future research will focus on extracting more information from the artifacts we already have. The cordierite piece from the Greenland burial, for instance, could undergo a new generation of non-destructive testing. Sophisticated spectroscopy and residue analysis might detect microscopic patterns of wear or polish on its surface that are invisible to the naked eye, patterns that could confirm it was repeatedly held and rotated in a specific way. Similarly, if other potential candidates are found, analyzing the trace elements within them could geochemically fingerprint their origin, telling us precisely which quarry they came from and mapping them onto known Viking trade routes. This would provide powerful circumstantial evidence, demonstrating that these specific types of crystals were being deliberately sourced and transported, rather than simply being pretty rocks picked up at random. A particularly exciting frontier involves experimental psychology and sensory history. Researchers are keen to understand not just if the sunstone worked, but how it felt to use it. How did a navigator train his eye and brain to perceive the subtle variations in light intensity or color shift? Were there specific cognitive techniques or mnemonic devices passed down orally to help interpret the crystal's signals? Modern experiments could involve training subjects over months or even years to use replica sunstones, tracking their improvement and developing a deeper understanding of the exact skill set required. This moves beyond proving the physics to understanding the human experience, reconstructing the mind of the Viking navigator as much as his tools. The biggest unanswered question may be one of scale and distribution. Was this a widespread, commonplace technology, or a rare, specialized secret known only to a select few? The answer would fundamentally change our view of Viking society. If every major vessel carried one, it suggests a broadly shared, technical understanding of optics. If it was a rare treasure, it points to a culture where immense power and prestige were vested in a small class of elite experts who guarded their knowledge closely. Future discoveries of ship burials or settlements linked to famous navigators could hold the key, revealing whether these tools were as common as a hammer or as rare and revered as a king's sword. The mystery of the Viking sunstone is far from solved. It is merely entering a new and even more fascinating chapter, where science, history, and a touch of ancient magic continue to collide. If you're feeling inspired to connect with this ancient art yourself, the first step is finding the right crystal. Your best bet for an authentic experience is to seek out a piece of Iceland spar, also known as optical calcite. This specific form of calcite is prized for its perfect transparency and dramatic double refraction. You can often find small, polished specimens from mineral dealers online or at gem and rock shows. While a large, flawless block like the one from the Alderney shipwreck is rare and expensive, a smaller, clear piece about the size of a large coin can work perfectly well for experimentation. Alternatively, you can look for cordierite, often sold under its gem name iolite. This stone is famous for its strong pleochroism, meaning it will show different colors, typically a violet blue and a pale yellow gray, when you rotate it against the light. Either of these crystals will allow you to directly experience the optical properties that made the sunstone so valuable. Once you have your crystal, the real exploration begins. Start on a day with a clear, bright blue sky. Find a comfortable spot and hold the crystal up to your eye, slowly rotating it in a full circle. If you're using Iceland spar, you'll immediately notice its incredible property. Everything you see through it will appear doubled. Focus on a distant, sharp object like a telephone pole or the corner of a building. As you turn the stone, watch how the two images move, converge, and separate. The goal is to find the angle where these two images appear exactly equally bright. This point of balance is the crystal telling you the orientation of the polarized light. With an iolite crystal, the process is slightly different but just as fascinating. Rotate the stone and watch for a dramatic shift in its color. You're looking for the point where the blue is at its most intense and saturated. This deep hue indicates the crystal is aligned with the polarization pattern of the sky. After you've practiced on a clear day, wait for a day with high, thin clouds or a light haze. This is where the magic truly happens. Even with the sun obscured, that hidden pattern of polarized light is still present in the sky. Repeat the exercise, but this time, try to locate the sun's position without looking directly at it. Use the crystal to find the bearing, make a mental note of it, and then uncover your eye to see how accurate you were. This simple act of discovery, of seeing the unseen, is a powerful way to bridge the gap between modern life and ancient wisdom. It's not about navigating the open ocean, but about training your perception to notice the subtle visual cues that most of us ignore every day, connecting you to a time when human survival depended on this intimate dialogue with the natural world. Yet to view the sunstone as merely a clever trick of the light is to miss its true significance. It stands as a powerful testament to the core of the Viking spirit, a relentless, pragmatic ingenuity born from the need to conquer an unforgiving world. This was not innovation for its own sake, but a targeted, brilliant form of problem solving. They looked at a seemingly insurmountable obstacle, a sunless, starless, featureless seascape, and refused to accept defeat. Instead, they turned to the very elements that challenged them, discovering a hidden map in the sky's diffuse light and a key to read it in the Earth's crystals. This same practical genius is the thread that runs through all their greatest achievements, revealing a culture far more complex than the popular image of raiders with horned helmets. This innovative mindset is nowhere more evident than in their revolutionary ship designs. The iconic longship was a masterpiece of naval engineering, perfectly adapted for its dual roles of exploration and raiding. Its shallow draft allowed it to travel far up rivers and land directly on beaches, enabling the lightning-fast strikes that terrified coastal Europe. Yet these same vessels, when configured as broader, deeper cargo ships, were robust enough to withstand the monstrous waves of the North Atlantic, carrying families, livestock, and everything needed to establish new settlements across the sea. This wasn't just boat building. It was a sophisticated application of hydrodynamics, woodworking, and modular design principles. Each curve of the hull and overlap of the clinker-built planks serving a specific purpose for speed, stability, or cargo capacity. The sunstone was the navigational counterpart to this maritime technology, a sophisticated tool for a sophisticated seafaring culture. Their legacy, however, extends far beyond the ships themselves and into the vast network of connections they forged. The Viking Age was fundamentally an age of exploration and cultural exchange on an unprecedented scale. They were not just takers, they were facilitators of a globalized medieval world. Their trade routes became arteries of commerce and ideas, stretching from the bustling markets of Baghdad, where they traded furs and amber for silver and silk, to the rugged coast of Newfoundland, where they encountered indigenous peoples centuries before Columbus. In the east, they established the ruse trading posts that would eventually evolve into the foundational states of Russia and Ukraine. In the west, they settled and reshaped the cultures of Iceland, Greenland, Ireland, England, and Normandy. The Sunstone was the critical enabler of this expansion, providing the navigational confidence to push beyond the horizon, to trust that even in the most disorienting conditions, a way forward could be found. It was the key that unlocked the Atlantic, turning a barrier into a highway. Ultimately, the story of the Sunstone is a profound lesson in adaptability. The Vikings thrived because they were unparalleled observers of their environment, learning to read the messages written in the waves, the stars, the flight of birds, and the very light of the sky. They didn't seek to dominate nature with brute force, but to understand its rules and work with them, using whatever resources were at hand to craft elegant solutions. In an era often dismissed as the Dark Ages, they were pioneering experimental scientists, harnessing the physics of light centuries before those principles would be formally defined. Their legacy is a powerful reminder that true innovation is not always about inventing something entirely new, but about perceiving the potential in the world around us in a simple crystal, a pattern of wind, or a shared story, and having the courage to use that knowledge to voyage into the unknown. So where does this long and winding journey leave us? After sifting through the sagas, the science, and the spirited debates, a compelling picture comes into focus. The sheer weight of evidence, from the matter-of-fact saga descriptions to the proven physics of crystal optics, and the later archaeological find at Alderney, points to one inescapable conclusion: the Viking Sunstone was almost certainly real. It wasn't a mythical artifact or a mere literary device, but a sophisticated, purpose-built instrument born from a deep and observant relationship with the natural world. The Vikings didn't possess magic. They possessed something far more powerful, a profound understanding of their environment and the ingenuity to harness its hidden laws. They looked at a featureless gray sky and saw not an obstacle, but a puzzle to be solved, discovering a celestial map written in the very nature of light itself. This story is about so much more than just how they crossed an ocean. It's a masterclass in human resilience and adaptability. Confronted with one of the most daunting environments on Earth, the Vikings didn't retreat. They observed, they experimented, and they innovated. They turned a common mineral into a precision tool, their keen eyesight into a scientific sensor, and their accumulated knowledge into a living guidebook. The Sunstone represents the pinnacle of this adaptive genius and the ultimate tool for the ultimate challenge. It symbolizes humanity's relentless drive to explore, to push beyond the known horizon, no matter how fierce the storm or how thick the fog. It reminds us that our greatest inventions are often born not in comfortable labs, but in the teeth of necessity, forged by the urgent need to survive and understand the world around us. Now, I want you to take a moment and truly picture it. Close your eyes and imagine yourself standing on the deck of a Viking longship. The wood is cold and wet beneath your feet, the air is heavy with salt spray, and an impenetrable wall of fog has swallowed the world, leaving you adrift in a silent, gray void. The only sounds are the creak of the hull and the anxious whispers of the crew. In your hand, you hold a smooth, cool crystal. You raise it to your eye, your movements slow and deliberate against the ship's roll. You turn it, patiently scanning the emptiness, your entire being focused on the subtle play of light within the stone. And then you see it, a shift, a balance, a faint blue hue, a signal cutting through the gloom. In that moment, the void has a direction. The unknown becomes a path. You are no longer lost. You are guided by a sliver of hidden sun, a thread of certainty woven from ancient wisdom and the immutable laws of physics. That feeling, that breathtaking convergence of human courage and natural wonder, is the true legacy of the Viking Sunstone. It's an invitation to all of us to look closer, to question deeper, and to never stop seeking the hidden patterns that guide us through our own uncharted seas.